All right, before we start on today's lecture, I haven't mentioned it up until now, and that's sort of been an oversight. There is an additional handout on the M drive that's going to start to become more and more useful to you. What is it called? I'm looking at it on another screen. Registersummary.excel. All right. Just like the opcode handout was the magical, Rosetta Stone of all assembly instructions, this is something I put together for you. Need to be on the right monitor to zoom. That gives you all of the pertinent bit positions of all of the registers of all the peripherals we're going to use. So having this is a shortcut to having the 650-page manual open. It's not going to tell you everything. For example, do you know what CS stands for inside of this register? Everyone who's done the lab should know what the CS bits do. Clock source, yeah. The WGM bits, what do they stand for? Wave generation mode. Okay, that's good that you know that, because that's all we're going to be doing today is more of the same. But it's useful because this tells you, what does it mean that there are two addresses here? No, it's not high and low. In and out versus STS LDS. So something to consider there. All right. With that said, let's get to today's slides out. Yeah. Yeah, those are things I have not assigned. Those are kind of in there as a dump from other stuff. Okay. They're interesting to look at and try out, but that's more on your own time. All right. So today we go and revisit the timer subsystem. This is chapter 15 in your book. It's got a lot of good, fun examples and so forth. The reason I'm doing this now is because it directly relates to your next lab. Lab 5, you're going to be creating dual tones like you would hear on a old-fashioned telephone. Not so old-fashioned that you have to rotate it, but old enough that you have to press buttons that really exist in the real world, not a screen. So, waveform generating and capturing. We're going to talk a little bit about stuff that pertains to your lab in terms of what sound waves really mean and how we characterize them. Then we'll talk about timer 0 and all the timers and new stuff. Okay, when we first looked, there was a big block diagram of all this stuff in there. We've really only been focusing on just a little piece of it, and we're going to expand on that. So, a couple of things that you do need to know. Any of you ELEs will get used to this pretty quickly. Things like the frequency of a waveform. We're generating square waves with our digital logic. The period and frequency of a wave are inversely related. So if you know the time in seconds that a waveform from rising edge to rising edge or falling edge to falling edge, you know its frequency by doing 1 over the period. The duty cycle, okay, which we're not really going to get into today, but good to know, is the percentage of time that it's on versus the percentage of the time that it's off. Okay, so if you have a 50-50 duty cycle, that means it's on 50% of the time, off 50%. 30-70 would be on 30, off 70. And finally, amplitude. Amplitude, again, we don't really have control of right now because we're on a 5-volt logic device, so our amplitude is 5 volts, but it's the distance in volts peak to peak. Anybody know what this is? It's a keyboard or a piano or some representation, but it's got a lot of stuff going on here. Along the bottom, I have the names of notes. Okay, notes typically go from A to G and then repeat. The number after it, here I've got G7. Okay, G7 means in the 7th octave. Down here I've got C4, that's in the 4th octave. Every time you go up an octave, you double its frequency. And if you double the frequency, what does that mean for the period? If you double the frequency, you half the period. That's right. So that means that as your frequency goes up, that square wave gets scrunched closer and closer together. And as your square wave gets Stretched, what does that do to your frequency? As it. Frequency gets lower and lower and lower. Low frequencies tend to be more deep bass sounds, and higher frequencies are sort of higher voice sounds. Okay, that's my musical ability right there in a nutshell. That's where we're going to stop that. That's all fine. This is for music people. They read this, they understand this. We look at these numbers up at the top. These numbers are a frequency in hertz. Hertz stands for cycles per second. A cycle, where's my little marker here? A cycle is a low and a high pulse. So in between these dashed lines, that's one cycle. So if you have some number of cycles per second, that is your frequency measured in hertz. So for example, the A4 note. Where's mine? It's not working. Hold on, delay game, 5 yards. Am I throttled because of my power supply? That wouldn't be good. Nope, looks fine. All right, it was just being a little strange. Let's try that again. Nope, still not working. Okay, I'll have to point. A4, right there, is 440 cycles per second. Thus far, we've not talked about the 328p once this class. We've only talked about music, frequency, period, and frequencies in hertz. If I go up one octave from A4, 440, here's A5, it's 880. So music, every octave you go up, you double the frequency. If I look at one of the more interesting ones, not quite nice round number, but let's say C4, stands for middle C, that's 261.63 hertz. If I go up to C5, I've got exactly double that, 523.25 hertz. Near enough. Okay, so music is usually defined in terms of notes. Notes are directly correlated to frequencies. All right, now we get back to the Atmega series. So this is the Atmega 32. It's got timers, and we've really only dealt with the stuff on the left. Output compare register, comparator, free running counter, and flag. But there's all this extra stuff. And that's the 32. In the 328p, there's even more stuff. Really the only difference here, though. Okay. Timer 1 is exactly the same in both. Timer 0 and timer 2 in the 32 just have a single green box which says waveform generator. In the 328p, all of them have 2 boxes. So let's zoom in just for now on timer 0. Okay. Here is a nice pretty picture of the block diagram for timer 0, along with our registers. And of course now you can see, oh, I spoke too soon. You could see it for just a second. Along with the registers. And we've dealt with only parts of this. The CS bits, which again stand for clock source, the WGM bits, which stand for wave generation mode. We've dealt with those, and we've seen that there are some settings that we use. All the stuff on the right side of this diagram has to do with waveform generation. There's this magic box that deals with all of the interesting signals that it will receive about when things have reached the top or when they've reached OCR. And they can control physical pins. So on the far right there, you see that we've got 2 special pins called OC0A and OC0B. Those are the outputs of the waveform generation unit, and they are mapped to pin D6 and D5. In fact, you can even see the control logic here for D5. This right here, there's DDR, the DDR bit. And there's the tri-state buffer associated with the DDR bit. Normally, we just go right from port D5 through to that tri-state buffer and out. But now there's some new hardware that we've added in. We've added in, what is that fun trapezoid? Happy little trapezoid? It's a mux. So now we're choosing, we're selecting data. Either we're going to get our information from the waveform generator, or we're going to use port D5. All right, let's just go over a review of what we normally do with timer 0. So first off, we've seen the clock source bits, okay, or clock select bits. It's just a prescaler. Timer 0 can also take external events, which we haven't really used very often, but something to remember that we can do. Those 3 bits stand for our clock source as a prescale from our system clock. The waveform generation mode bits, typically we've only used the ones I highlighted in pink, normal and CTC mode. Okay, we're going to continue using those modes. I know I highlighted yellow, fast, PWM, but we won't do that just yet. We're going to continue using just these 2 modes, but we're going to add in some extra stuff. So all right, so this is for the 32. It's the same stuff, but the registers are arranged a little differently. Okay, so in normal mode, right, this should be reviewed. This is the same slides from before. Stuff counts. I've even got my fun animation. Counts up to FF. When it hits FF, the flag is set. And we've since learned, since we did this chapter the first time, that an interrupt can also fire when that overflow happens. Now, CTC mode, same stuff, except now we don't have a fixed top value. Okay, when it counts, whatever value is in the output compare register, that's what we'll count to and then reset. And again, we can trigger an interrupt. Something can happen. Now, the waveform generation hardware does something every time an event happens. We can tell it what to do, but it's going to do something. This right here is what we've thought of as the I/O hardware. Data direction register controls this tri-state buffer. We've got a D-flop for the port register. So when you write a 1 to the port register, it puts out 5 volts. When you write a 0 to the port register, it puts out 0 volts. But on certain pins, there's this added hardware. This added hardware is driven by the waveform generator. Waveform generator has tons of inputs. Some of them are the waveform generation mode bit. We've got these COM bits, which we have not dealt with before. These are new today. And also, whether or not the free running counter is at the top or the bottom. The last one here, called FOC, is just stand for force output compare. We've never had to use that bit before. It is one of the bits we'll talk about today. It stands for force something to happen. Okay, so the COM bits are actually the most interesting. The COM bits live inside our control register TCCR 0A, okay, or 1A or 1 or 2A. That's where they live. And for each channel, we have 2 bits. So the way we read this is COM 0. That means it's the COM bits for timer 0. The A means we're on channel A. So we've got COM 0A and COM 0B. 2 channels worth of control. And finally, it's 2 bits. So it's 1, 0, 1, 0. Those are the most significant bits. Now, each of these combinations does something different. It tells the waveform generator to do something interesting. When you are in a non-PWM mode, which both normal and CTC modes are not PWM modes, okay, you can't see the bottom. Oh, no, that's all 4. No, you can't see the bottom of the screen. About as good as I'm going to get. Let me see if I can just move this up briefly here. Come on. Come over here. No. Move this up a bit. Move that up a bit. And return. Not much better. Okay. So for the COM bits, there's 4 different modes you can be in. Normal mode just means we're not doing any waveform generation modes. And that's what we've been doing thus far. We've just left these as 0. Once we want to do waveform generation mode, we have a couple of options. We can toggle every time a compare match happens. We can clear on a compare match, and sort of the hard one to see down here is set on a compare match. So if we toggle on a compare match every time a compare match happens, that's going to allow us to generate a square wave. And a square wave is good enough to create a basic tone. Okay. So when we are in normal or CTC mode, this table applies. Normal, toggle, clear, set. That's a little bit easier to see on the screen. So if we are in CTC mode, this is what's going to tend to happen as we change the value in the output compare register. If we have a large value in the output compare register, okay, which is at the bottom here, the time between output compare events is relatively large, which means our period is relatively large. What does that mean for our frequency? If our period is large, our frequency is quite low. If our output compare register value is smaller, that means the time between events will be smaller, and that means that the frequency will be higher. Now, in terms of calculating what your frequency is, well, that all depends on your system clock frequency and what you've put in the register. This N stands for your prescaler value. So if you're prescaling at 1 or 8 or 1024, that applies there. So if you want to calculate a given frequency based on what's in the output compare register, you take the output compare register value plus 1, because remember, the event actually happens when it resets to 0. That's what that plus 1 is for. So if you, yeah?
Can you explain what prescaling does in this sense?
So prescaling the clock makes the incoming clock change less frequently. Okay, so that has an effect. If the incoming clock is slower, what does that do for your frequency?
It means that it's also slow.
Let's take a look, right? So if this right now happens, let's just for the sake of argument say this is 1 millisecond, okay? If I divide my incoming clock frequency by 8, this is now 8 milliseconds, okay? So if your period is larger, what does that do to your frequency?
It is small.
Okay, so all we're doing here, the larger the prescaler, the more we're taking out of this system. So we're making the denominator larger, okay? Means overall we're going to have a lower frequency. So 2n, the 2 in this formula is because we need to account for 2 toggles. We're going to be high, we toggle low. Then we're going to be low and we toggle high. That is 1 cycle. All right. So with a little bit of algebra, we could rearrange this to calculate our output compare value for a given frequency. Okay. This goes more to what you were just asking, Alex. Depending on what your prescaler value is, will change what you want. So here I've actually rearranged, right? If you want a given frequency, say 500 kilohertz, and you are running at 8 megahertz system clock frequency, you end up with 8 divided by 1. So depending on what your prescaler value is, that changes what you put in. If your prescaler value is 8, that means you put a 0 into your output compare register. So it's going to trigger every time, basically. If it's a prescaler of 1, that means you can put 7 in there, so every 8 cycles. So you can see it's not that crazy, right? We just say 7 goes into our output compare register, and then TCCR0 equals 19. This is my pet peeve. What does 19 mean? Well, you have to look it up. What it means is that we've set our clock source to 1. We've set our mode, our WGM mode, to CTC mode. Okay. And furthermore, we've activated our COM bits. To say toggle, by the way, just a reminder, all of this applies to toggling our pin. Okay. So the only difference with timer 2 is just like timer 0, except the clock source bits. We've seen that before. This additional 128 and 32 clock divider allow us to get closer to our desired frequency. Because remember, there will be some error because you can only put integers into your output compare value. So if you have a floating point calculation in there, you're going to have some rounding error. Timer 1 is a little bit more interesting. Even though all three on the 328P, all three timers have two output compare channels, two waveform generation compare channels, there are a larger number of waveform generation bits. And if we actually go back a few slides here to this very crowded version, it's difficult to see on the screen right now. If you actually go into the PowerPoint on the M drive, you can see each one of these has different pins that it is associated with. Okay. And timer 0 and timer 2 have 3 bits of waveform generation. Timer 1 has 4 bits of waveform generation. So obviously we get something for that. Let's go and look at that. So there's timer 1. It's got 4 bits of waveform generation, 2 channels. It outputs to port D5 and D4. So what do we get for all those extra waveforms? Well, how many modes can we have with 4 bits? One more than that. 16. Okay, so here are our 16 modes. The ones that I've highlighted are the ones that we're likely to use for waveform generation. Normal mode or CTC mode. CTC mode in the first instance looks just like CTC mode in all the others. You put your top value into the OCR register, and then it goes off and it does its thing. The second CTC mode has an extra register, the input capture register, ICR1. And I know there's a lot of data on the screen. This is the kind of thing you would look up in a data sheet. We are not getting into any of the other modes. All of these other modes are PWM modes, pulse width modulation modes. We're not dealing with those yet. Maybe when we start talking about servos, we might return to those. But for now, we're just dealing with those 3 modes, mode 0, mode 4, and mode 12. Okay, and mode 4 and mode 12 are both CTC, clear on timer compare. Okay, the only difference is what the top value is. In the first case, mode 4, our top value is OCR1A, and in the second case, mode 12, it's ICR1. All right. Now this is a 16-bit timer, so it has a much larger range. We can have much higher top values, okay, which means we can get a lot better precision. All right, so then inside TCRs, okay, this is just saying there are 2 channels, and each channel gets its own setting for toggling. Okay. Questions so far? Okay, so if we're generating waveforms, it is almost as simple as setting up an interrupt. I say that because we do some setup and then we leave it alone. I'm gonna blank out the screen and talk for a moment. That'll be fun. So the screen didn't blank out, did it? Okay. So in the lab, the screen still didn't blank out. Okay, I'm just gonna not touch it. In the lab, you're expected to generate 2 tones depending on a bunch of keypad presses. Okay, so you're gonna have a 4x4 keypad. I might even have one in my bag. But of course, now that I've said it out loud, I do not have one in my bag. It's a grid of 4 buttons by 4 buttons. Your job is to create DT, DTMF tones, dual tone, okay? It's what you would hear on a phone. So when your typical phone dialing sign, all of those tones are slightly different. And that's how we originally used to get information across the phone line. You would press a button, there would be a chip usually that would decode those signals and turn it into a row and a column on your keyboard. So how wide and tall is a grid for a phone? 3 by 3 plus 1 is an interesting way to specify. Plus the 0, so it's usually 4 rows. What's to the left and the right of the 0? Pound and star. That's right, it is a pound. It's not a, whatever that other word is. Might be an octothorpe. Octothorpe is acceptable. So, yeah, in typically we had 3 columns, 4 rows. Unless you were a lineman. Lineman is a person who used to climb up the poles. And they would have a special lineman's handset, and it had extra buttons. The buttons it had were A, B, C, and D. So it had a 4 by 4 keypad, which is convenient because that's what you have in lab. Your job is to create, and this is where I'm gonna, it's gonna not blank again. Your job is to recreate those signals. So let's load up Lab 5 for a moment here. Recreate this. So this background here, we've already looked at that. That's the clock frequency, OCR value, the prescaler. It's already rearranged for you though. All right. This is the keypad that you're going to be using. This keypad is just 16 buttons, but instead of needing 16, of course, now let's go, let's make my face smaller on the video here. There we go. So there is the keypad. It's a 4 by 4 matrix, and it's put together in a very interesting way to reduce the total number of pins that you need. All right. You're going to be using a scanning technique, which after this initial intro, I'll talk about how you scan through a keyboard matrix. Okay. Back to this screen. Your job is to create 2 sounds. So one sound is going to come out of OC0A. That's timer 0. One sound is going to come out of OC2A. What I've put in here is just a little mixing circuit. It's going to go to a buzzer. So you're going to get for this lab a keypad and a buzzer. You can pull resistors out of the stockroom drawers. Okay. That's really all the physical stuff that's required. In terms of the software, this is how handsets used to work. Every column was assigned its own frequency. Every row was assigned its own frequency. And if you look, it starts at 697, goes up to 941 for the bottom row, and then the columns continue to increase. I don't want to get into the history of why they did this, just this is what it is. These are the frequencies you have to create. There's going to be a bit of math. Okay. Furthermore, you need to be accurate to within 1% of your frequency. So when I look at this on, say, the spectrum analyzer on your analog discovery board, I want to see a peak that is 941 hertz, not 943, not 939, 941 hertz. So when you do your calculations, and again, the formula is fairly straightforward. Come on, formula, straightforward. Here we go. There it is. Figure out what's your system clock frequency. And what is your system clock frequency? 16 meg. Then you choose your prescaler value and your OCR register value, and that gives you your output square wave frequency. Question? No. Okay. So you can rearrange this, I'm fairly confident, to solve for your OCR frequency given a desired frequency. And your desired frequencies, again, come on, are here. Okay, those are your desired frequencies. Now, what I recommend you do is create a table. This is the kind of stuff that Excel is really good at. And I'm glad I paused in the middle of that sentence because I was about to say, this is the stuff that Excel excels at. Which is just a little cheesy. So what I've done here is I've set up timer 0 and timer 2 and the frequencies that you might want to use. You should calculate the periods. What is the period of 697 hertz? How does period and frequency relate to one another? They're inverse. So to calculate the period, 697, actually I'll do it like this because I'm lazy, to the negative 1 power, 1.43472023 milliseconds. Is that right? Yeah. 1.4 milliseconds. Now, that is a number that is not going to be easy to exactly approximate. So once you calculate the period, then you can calculate what your OCR values need to be. And I put in the 32 and the 128 column, but those are not available for timer 0. They're only available for timer 2. Once you do this, remember these numbers, these OCR values must be integers. So if you calculate, and for example, let's say that's 1 6 6 divided by 6 7 1 divided by. We thought class was just going to be me grunting for the day. Okay, not percent sign. Not delete. All right, I give up. Calculator's making me angry. Excel is a little bit nicer than this because you can just apply it and you can move the formulas around. You're going to want to calculate the error, the percentage error that these will give you. So, for instance, you will find a number for 256. It will be some number because math will always give you a number. It's your job to associate that number with something that makes sense. So if you get 3.7 here, you can't put 3.7 to an OCR register. You can put 3 in, you can put 4 in. Probably 4 is closer. Okay, so put 4 in here. Then calculate the reverse. If you put 4 into the OCR register with a divider of 256, what frequency do you actually end up obtaining? Is it close enough to 852 hertz to pass muster, to calculate your percentage error? Okay. This is also split up into, multiple phases that you can do. Start by just hook up a single button, and conveniently B7 is a button already on your board. Anytime you press that button, set it to generate a tone, fixed tone, doesn't matter what tone, any tone. That'll make sure that you've hooked up your buzzer correctly and make sure that you can, trigger a frequency on the waveform generator. Phase 2, okay, is implementing row and column scanning. How am I doing on time here? Okay, we've got enough time to actually look at row and column scanning. In the book, there is almost directly copyable code. There are a few things that'll need to change, but almost directly copyable code that you can use to scan a 4x4 matrix. I highly recommend you look at it as part of your research. That's phase 2. Okay? Only use one timer for this part. Just find the row or the column, your choice, but play one frequency. And so check all 4 columns. Do you get the right frequency for each column? Finally, phase 3, or not finally, but phase 3, phase 3 is the final phase. That's where everything comes together. You'll generate one frequency on timer 0, one frequency on timer 2. Send them both out to the buzzer. Okay? Now, in terms of the keyboard, Keyboard is not something we have explicitly covered yet. And I want 12, I think. Oh, I didn't want to open it from the M drive. I have it on my machine. Okay. Chapter 12 is LCD and keyboard interfacing. We're going to skip the LCD right now. We'll come back to that at a time in the future. Okay, the keyboard. This part of the lecture tells you how to do the keyboard part. It's not that crazy. So to start with, we've done buttons. We've done a single button. If you wanted 16 buttons, you could do it with 16 I/O ports. But if you did it with 16 I/O ports, you wouldn't have many I/O ports left for anything else. Oh goodness, it's going to animate. Wait a second. Wasn't it just supposed to go low? What's the stuff in red? What's happening there? It's either going to be connected or disconnected. Why would it go high after it's gone low? Let's assume that this piece of paper is our button. It's a flat metal plate. It'll touch the top of this, and then it'll make contact. That'll complete the circuit. It's just a metal switch. The problem is metal has a bit of flex to it. So if your metal is like this, it'll tend to oscillate a little bit before it finally settles into its down position. And the same thing will happen when you release it. It'll oscillate a little bit until it's finally up. This is what's called bounce. The idea is, even though you think you have a perfect switch, we don't live in a perfect world. We live in the real world. So there will be this thing called bounce, where it will oscillate for a little while. Now, the little while is a relative term. Could be a couple of milliseconds, could be a few hundred milliseconds. Depends on how crappy your button is. Okay? But that's something that you do need to consider with this kind of keypad. Dealing with bounce isn't all that hard. The first time, this right here is waiting for while something is 0. Sit there and do nothing. Once it becomes 1, it delays and waits while it is 0. Here, this waits while it's 1. This is effectively waiting multiple times. It's reading it multiple times and delaying 20 milliseconds in between. So it's waiting for it to be consistent. All right. So the idea here is we wait while it's 0. We delay 20 milliseconds. We check if it's 0 again. As long as it's 0, we stay here. Okay? Once it's done, we say, while it's 1, sit here and wait. Okay? And we're going to continue waiting as long as it's 1. Once it's been both 0 and 1, then it will add to a variable. The idea here is we're debouncing this button by checking it multiple times with a time delay in between it. All right. Think about debouncing as we're doing this. We'll go through other ways once we get to the keypad matrix. So, yeah, okay, we can do 16 buttons. We've said that. But more often than not, if we buy a keypad matrix, whether it's a membrane keypad, which is kind of those soft feeling buttons, or a keypad like we're going to have, which is just discrete hard buttons, we use a multiplexing routine. Multiplexing as a term should be familiar. The idea is we're going to scan through each of these rows and columns. So here's an example interface you might have. You might have 1 through 9 plus 1, Jimmy, for the 0. But instead of star and octothorpe, we have cancel and OK. And then, maybe up, down, left, right. Sure. The way we do this, though, is with 2 groups of 4 pins. Now, each of these buttons is really just a single pole, single throw button. It's either connected or it's not. Okay, looking at just the hardware here, you start out with the buttons, and you connect one side of all of the buttons that are in a particular row together. So they're all shorted together. Each row ends up with its own bus of buttons. Then, on the other side, on the columns, the other sides are all connected together in columns. Okay. Now, if you press any one of these buttons, I didn't do that. It's good to know, though. Okay, the last piece of this is pull-up resistors, which you will be using the internal pull-up resistors inside the 328P. What's going on here? If I press a particular button, this guy right here, what I'm going to be doing is shorting these two lines together. This column line will be shorted with that row line. So, I'm going to use all of my rows as inputs. I'm going to be reading those in, high impedance inputs. I'm going to be using all of my columns as outputs. So if I output a particular value, okay, for example, let's say I output a number, well, rather a voltage, 5 volts, to this line, okay? If I output a voltage to that line, that column is 5 volts. However, until I press one of the buttons in that column, the inputs will not see anything. So in this diagram, I've actually pushed, I don't know if you can tell, that upper left button. So because I've done that, okay, I'm going to have a direct connection here. Now I said drive it to 5 volts, which does make a lot of sense because if I drive it to 5 volts, I've already got VCC on the other end of this, don't I? So what actually is going to be happening is we're going to be doing it the reverse. We're going to be active low. I'm going to ground this terminal. So it'll be grounded. This is pulled up normally. So when I do this, it will actually connect me to ground. All right. If I were to press a button that wasn't grounded, say this button, I would see 5 volts here because it's pulled up. All right, so let's look at this a little more. The way we're going to hook this up is we're going to use a group of 4 bits and a group of 4 bits on the AVR. When we write our software, there's 2 jobs we need to deal with. First is, are any keys pressed? Any of the keys pressed at all. Once we know if a key is pressed, then we want to know which key is pressed. Detecting if any key is pressed is actually pretty simple. Okay? So for now, I'm using the 32. What I'm going to have here is my pull-up resistors enabled, and I've got port A and port B. So right now, I'm going to ground all of port A. So I've output zeros to all of those. It's a little bit easier to see this way. So you can see the brown representing ground. The pull-up resistors are pulling up all of the columns high. So I'm reading in on port B, and what do I see? Right now I see F. Okay, I see 1, 1, 1, 1, because none of the buttons are pressed. So in this case, my port B is my input, port A is an output, and I'm outputting all zeros. What happens if any of the keys are pressed? Well, let's press the upper left-hand one. By connecting this together, I've got 5 volts above the pull-up resistor, but this is now shorted to ground, which means I no longer see F. That's all there is to detecting keys. You put out all zeros on the rows. You look at the inputs, and these are pulled up inputs. This is going to be with a pull-up resistor. Okay. And if you see F, that means no buttons are pressed. If you see anything else, it means there is at least one button pressed. Now, right now D3 is grounded. What would happen if in addition to pressing this button, I also pressed this button? What other lines would change? And what would they change to? D1. So are you talking about this D1 or that D1?
This D1.
This port A is D1. All right. Well, we're actually driving that. So we're driving that with a 1. Oh, sorry, a 0, a ground. So if we press this, we'd have ground on this side, ground on that side, nothing changes. Okay? This is still ground because of this button. None of these other columns are affected. So this tells you that at least one button is pressed, but not how many, because you could have all of these pressed all at once. Does everybody see why that's a thing? Right? If you pressed all of these, you wouldn't know. You would still see on your input 7, 0, 1, 1, 1. Now, what would it mean if you read, these were grounded, your outputs were grounded, and you saw a 2? What would that mean? 0, 0, 1, 0. What would that mean? How would you have to manipulate the keypad to get that to appear? No, go ahead. D3, D2, and D0 are currently 0 in this hypothetical situation we're talking about. So what buttons could you press? Do it like Battleship. A, B, C, D, 0, 1, 2, 3.
So currently with no buttons pressed, we'll have 1.
If no buttons are pressed, you'll see 1, 1, 1, 1. Correct.
So on port A, D3, E2, and D0, there's at least one button pressed.
So port B, there's at least one button pressed in this column, and this column. Furthermore, we know that no buttons are pressed in that column. We don't know how many are pressed. There could be as little as 3. Could just be that button, and that button. Or it could be as many as 12. All 8 of those and all 4 of those are pressed. Okay. That is an option. So detecting if a key is pressed, pretty simple. You can do it in 2 lines. Well, 3 lines. There's a no op in there. We'll talk about that in a second. All we got to do is look for something that isn't an OXF. Yes?
Could you find out which row was pressed by multiplexing port A
Well, you're getting a little ahead of me. That's the key detection part, which key is pressed. You could have done the same thing if you had grounded all of these all of these columns, and then read in the rows, and that would tell you which row. But that's not how we're going to do that. Okay. So how do we identify a key? It's pretty similar to what we just talked about, what you just kind of hinted at. What we're going to do is we're going to scan through each of these rows by setting setting D3 to ground. So what I've got here right now is I've got a key pressed here, here, there, there. So I've got a total of 4 keys pressed in this hypothetical scenario. And what we're going to do is we're just going to look at what happens at each of these options. We're going to go through grounding one at a time. So in the case where I've grounded this row, I've got pull-up resistors, I'm still using these as inputs. Okay? By grounding this, and this button is pressed, I receive a 0 here. There's no button pressed here, so I receive a 1. There is a button pressed here, so I receive a 0. And finally, in the last column, no button pressed. So by looking at this, I have grounded I've grounded row D3, and I received a 0, 1, 0, 1. That tells me that in column D3, tells me in row D3, column D3 and D1 have a button that has been pressed. That tells me just that row, though. So next, I have to swap. I have to ground these. There is a little animation that's playing here. You can see where the grounds end up going. But I might have to press it one more time. Nope. So in this case, there is a button that's pressed, so I receive a ground on D2. So by looking at this, I see 1, 0, 1, 1. Any place I see a 0, I know that that column has been pressed. Let's play a little game of prediction. I'm about to show an animation where D1 is grounded. Somebody volunteer what you think this will read. 1101, because this is unpressed, unpressed, pressed, and unpressed. Let's see. We ground the row, that grounds everything. The fact that that button is pressed causes D1 to go low. It's a very subtle animation, isn't it? But that is what happens. If you're having trouble wrapping your head around this, I really recommend you go and look at this and watch the animation, because it does show exactly how things are happening electrically. This button shorts this whole column to this row. As a result, we see a ground state on D1. All right, someone else want to tell me what's going to output on D0 when we ground D0? 1111, because none of the buttons are pressed. Yeah, it grounds and nothing happens. Okay. So if we want to write a function that's going to deal with this, write a function that waits for a key to be pressed, then returns the code of the key pressed. We have to define what code is, what buttons correspond to what. Okay? Here it is. This is how you start. First off, ground all the rows. Read all the columns. Open, meaning all ones. Are all the keys open? If it is, come back, read all the columns. I think that might be swapped, or I'm reading it wrong. So keep reading the columns till it's open. Debouncing is going to occur here. We do have to debounce. We want to check if the keys are solidly pressed. Once we've done that, then, I see, this is actually part of the debounce. First, we wait for no keys to be pressed. Once all the keys are pressed, or once they're all unpressed, then we sit here and wait for the keys to be down. So that's the debounce. Okay, fine. We wait again, read all the columns, are the keys down? So this is the debouncing part of the routine. Green waits for the keys to be unpressed. Cyan waits for the keys to be pressed. On the far right, this is where we do our keypad scanning. We ground the next row, which the first time through is going to be the 0th row. Read all the columns. Are there any keys pressed in this row? If there are, you look at the bit values to figure out which one is pressed, and you get the code from the table. The table is going to tell you what's going on. Now, where is the table that we're working from, page up, is this table. Now, if you look in your book, there are code examples that will actually give you the character values for all of these things. It might be interesting, okay, to set up your UART to send these characters over as an additional debugging method. So every time you receive a key press, send that character over the UART. It's not required for the lab, but might be really helpful in debugging. Okay? So it actually has code in the book that will return a character, an ASCII character, based on a key press. That said, the code in the book isn't going to work for you perfectly for the following reason. That's not the... Where do we go? There it is. All right. I don't know why that didn't work before. It's not going to work for you because of the fact that timer 2 needs port B3 and D3. B3 and D3. Timer 0 needs D4 and D5. The code in the book uses port D for everything. The whole port D. So if you're going to do this, you're going to need to do some bit manipulation. You might want to use port C for the row. You might want to use the upper half of port D as the column, or vice versa. Find 2 groupings of 4 contiguous bits, and you'll be pretty happy. Keeping in mind that these pins are already taken. B3 D3, D5, and D4. You don't have to use timer 1 for this. Okay? So there's a little bit of math involved at the beginning. You're going to have to figure out what prescaler you want for which frequency. When you press a button, okay, you're going to have it set up so that some kind of either you're polling constantly or there's an interrupt. Your call. One way may be easier than the other, depending on how you implement it. So this is a much more open-ended type problem. You are given a bunch of things, told to hook them together and make noise. It should be fun because, you don't have to use my frequencies to start. If you set it up correctly, you can just have a lookup table of frequencies or a lookup table of OCR values. So if you're kind of cutesy, you can set it up and you can play the piano on your little keyboard matrix as a test, or just because you want to. Okay, questions on the lab? All right. Again, if you came in late, this is a document on the M drive. It's 2 pages or 1 page single-sided. It's all of the registers associated with the 328P. It's just the names of them. It doesn't have their descriptions, but that's why it's really important for you to get used to talking about these things. So the CS bits in the timer stand for clock source. The WGM bits stand for the COM bits. Compare output mode. If you're using the waveform generator, what mode are you in? Okay? It doesn't tell you, for example, for the CS bits, doesn't tell you which prescalars correspond to which bit values. Got to have that. Got to be able to look it up. Okay? I know that 0 is off, 1 is unprescaled, and then maybe I could work through it. Like there's 8 and 64 and 256 and 1024. So you can start to you can familiarize yourself with it. The COM bits, I know that 0 is disabled, and then I know that there is toggle, set, and clear. I don't know which one is toggle. I got to look it up. But at least I know where it goes. So you can write yourself some boilerplate code that says, all right, TCCR 0A. I know that I've got COM 0A, COM 0B, and the waveform generation mode bits in there. I know that in TCCR 0B, I've got force output compare, one of the WGM bits, and the clock select bits, or the clock source bits. So you know what you have to fill out, and you can go through, check them off, all right? That's all you have to do. When you're writing any program, if you're using a particular peripheral, just look at each grouping of bits. Force output compare, don't know what those do. Look it up in the manual. Oh, force output compare does a toggle. All right, well, I don't need to use that. WGM bits, okay, I look up my table. Where's my table here? I don't know why I can't. There we go. Look it up in my table here somewhere. There it is. There's my WGM bits. Which one do I want? Oh, I want CTC mode, so it's 010. There you go. You know what you need to write. All right. I highly recommend you get started looking at that keypad scanning matrix code. It is, again, in chapter 12. It might be, there is a folder on the M drive called book code. It is separated into chapters. Chances are one of these, that's LCD. 12.7, that's also LCD. This is in assembly. That's an assembly code. Would have thought. No, that looks like LCD as well. There are codes. It might not be here. I don't promise that, but I thought it was in here somewhere. You can go and look through those. Those are code examples right out of the book. So when it says 12.6, that's example chapter 12.6. I typed them out for you so you can copy and paste a lot of this stuff. Again, the caveats involved are you have to make sure that you're using in and LDS correctly and out and STS correctly. You have to make sure that you've named your bit values correctly. So in the case of the 32, the bit values were a little bit concise. It wasn't called CS. It's a good example here. We didn't have force output compare 0A and 0B. We just had force output compare because there wasn't two channels. So it's something to look at. So you can convert these over to 328p compatible code relatively quickly. All right, I guess I'll let you out a little early today, unless there are any last minute questions for the whole class. On Tuesday, lab 4 is due, and we start lab 5. Okay?